Welcome to these gentle, soothing stories for sleep. I'm so glad you are here. Whether you are preparing to drift off to sleep, relaxing after a long day, or simply seeking a quiet companion, you have come to the right place. Tonight, we begin a journey into a world of stillness and profound beauty, a world of patient power and delicate design. We are going to explore a world locked in ice. Before we begin, I would love to know where you are listening from tonight, or perhaps how your day was. Please feel free to leave a comment below. Wherever you are, I hope you are feeling comfortable, relaxed, and ready to explore something gentle yet truly extraordinary. And if you find these soothing scientific journeys interesting, or peaceful, or even just wonderfully curious, please consider liking this video and subscribing to the channel. It helps more souls who are searching for quietude find their way here. Now, find a comfortable position. Let your body feel heavy and supported. Let your breath be slow and easy. Our journey begins high above the world, in the cold, silent theatre of the upper atmosphere. Imagine, if you will, a single speck of dust, so small it is utterly invisible, dancing in the thin, sunlit air. It is a particle of forgotten ash from a distant fire, or a grain of pollen from a flower that bloomed a continent away, carried aloft on the breath of the wind. To us, it is nothing, a mote of no consequence. But here, in the cold and the quiet, it is not empty. It is a seed. It is a promise of something beautiful about to be born. We follow this tiny particle as it tumbles and drifts through the rarefied air, an immense and empty ballroom where the dance of creation is about to begin. Around it, water exists not as a liquid, but as a transparent, invisible vapor, a ghost of the oceans and rivers far below. These water molecules are cold, so very cold, far below their usual freezing point, yet they remain as a gas, a supercooled vapor, restless and searching. They are waiting for a reason to change, for something to cling to, a place to begin their transformation. And then, one molecule, by pure chance, strikes our tiny speck of dust. And in that infinitesimally small moment of contact, a decision is made. The molecule stops its frantic gaseous dance and settles, clinging to the surface of the dust mote. It has found a home. This is the moment of nucleation, the scientific term for a beginning. It is the most crucial, yet most humble, step in the creation of a jewel. Just as a single word can nucleate a whole story, or a stray thought can crystallize into a profound idea, this microscopic particle of dust provides the necessary foundation for the water vapor to begin its transformation. Without this impurity, this tiny imperfection in the vast, clean emptiness of the upper atmosphere, the water vapor could remain a gas indefinitely, lost in its supercooled state, unable to become what it is meant to be. But now, with a place to start, the magic unfolds. Another water molecule arrives, and then another, and they begin to arrange themselves around the first. They are not arranging themselves randomly. They are following a deep and ancient law, a geometry written into their very being. You see, a single water molecule, H2O, is a marvel of elegant asymmetry. The large oxygen atom holds a slight negative charge, while the two smaller hydrogen atoms, perched on one side, hold a slight positive charge. This makes the molecule polar, like a tiny, weak magnet with a north and a south. And so, when these molecules draw near to one another in the cold, they behave just like magnets. The positive hydrogen side of one molecule feels an irresistible attraction to the negative oxygen side of its neighbor. This connection is called a hydrogen bond. It is not as strong as the bonds holding the molecule itself together, but it is a powerful and organizing force. As more and more molecules arrive at our growing crystal, they lock into place, guided by these hydrogen bonds. They huddle together for warmth, for stability, and in doing so, they form the most energy-efficient, the most stable shape possible. A perfect hexagon. It is like a group of dancers in a grand, cold hall. As the music of their thermal energy slows, they link hands and settle into a beautiful six-sided formation, the pattern that requires the least effort to hold. This is the fundamental reason why every snowflake you have ever seen, or ever will see, has a six-sided symmetry. It is the echo of the dance of molecules, the ghost of the hydrogen bond made visible to our eyes. Now our crystal begins to grow. It is no longer a speck of dust, but an embryonic jewel, a perfect, flat, hexagonal plate of ice. And it begins to fall. Its journey downwards, through the shifting currents of the sky, will be its autobiography. As it descends, it passes through layers of air with different temperatures and different amounts of moisture. These subtle changes guide its growth. The 6 corners of the hexagon stick out just a little farther than the flat faces, and because of this, they encounter more water vapor. More molecules latch onto these corners, so they grow faster, sprouting intricate arms. This process is called dendritic growth, meaning tree-like, because the snowflake begins to branch out like the limbs of a winter tree. If it falls through a particularly moist cloud, its arms will grow long and fern-like, with many delicate side branches. If the air is drier, it might grow into a more simple, plate-like hexagon, or perhaps a long, slender, 6-sided column. Every shift in its environment, every slight change in temperature or humidity, is recorded in the shape of its arms. The final, impossibly intricate form that lands on your sleeve is a perfect, frozen map of its journey through the sky. This is why it is said that no 2 snowflakes are ever truly alike. Each one is the result of a unique path through a unique set of circumstances, a frozen moment of atmospheric history. And so we reflect on this miraculous process. We began with a common speck of dust, an impurity, a flaw in the ether. And from that humble seed, through the fundamental laws of physics and chemistry, a form of almost perfect beauty and symmetry was born. It is a profound lesson from the quiet heart of nature, that the most exquisite and perfect forms often require a tiny imperfection to begin their existence. That the journey, with all its subtle shifts and changes, is what creates the final, unique beauty of the individual. Our single, delicate jewel continues its silent fall, one of many, a universe of crystalline art descending from the heavens. It is joining billions upon billions of others, each one a unique story, each one a tiny, frozen miracle. What happens then, when this soft, silent powder blankets an entire world, when its gentle, collective weight begins to quiet the deep, dark water below? Listen, in the profound stillness of a winter night. Can you hear it? It is not a sound you hear with your ears alone, but one you feel in the soles of your feet, in the hollow of your chest. It is a deep, resonant groan, a mournful sigh that seems to come from the very heart of the world itself. It is a sound of immense tension and slow release, a sound of something vast and powerful shifting in its sleep. It is the sound of a frozen lake, breathing. We find ourselves standing now on its surface, a great, solid expanse of glass under a ceiling of stars. The air is so cold it feels sharp in your lungs, utterly still and clean. The world seems captured, held in a perfect state of suspended animation. Below our feet is another world, a sealed kingdom of silent, green-tinted twilight. We can imagine the slumbering fish, the dormant weeds, a world held in waiting. And as we stand there, in the center of that immense quiet, we feel it again. A vibration that travels from the ice, up through our body. A slow, powerful pulse. The lake's glassy heartbeat. This solid surface we are standing on is a profound scientific anomaly, a miracle of physics that makes life on this planet possible. Almost every other substance in the universe behaves in a predictable way when it gets cold. As its atoms lose energy, they slow down and huddle closer together, becoming more and more dense. A solid piece of iron, for example, will sink instantly in a vat of molten iron. But water, our familiar, life-giving water, breaks the rule. As liquid water cools, it does become denser, but only to a certain point. It reaches its maximum density, not at its freezing point, but at a temperature of approximately 4 degrees Celsius. As it cools further, from 4 degrees down to 0, something incredible happens. It begins to expand. It becomes less dense. This is because of those same hydrogen bonds we saw in the snowflake, the gentle magnetic attraction between water molecules. As the molecules slow down in the deepening cold, The hydrogen bonds begin to assert themselves, pushing their neighbors away into that rigid, open, hexagonal lattice structure. There is more empty space in the structure of ice than there is in the jumbled, flowing chaos of liquid water. And because it is less dense, it floats. This simple, anomalous property has staggering consequences. If ice were denser than water, it would sink as it formed. Lakes and rivers would freeze from the bottom up, becoming solid blocks of ice in winter, extinguishing all the life within them. The oceans themselves would gradually fill with sunken ice from the poles, creating a runaway deep freeze from which the Earth might never recover. But because ice floats, it forms a protective sheet on the surface of the water. This layer of ice, perhaps a few inches or even several feet thick, now acts as a powerful insulator. Ice itself is a surprisingly poor conductor of heat. Once that initial sheet has formed, it shields the vast body of liquid water beneath it from the much, much colder air above. The air temperature might drop to a life-threatening -20 or -30 degrees Celsius, a cold that would kill any exposed organism in minutes. But just a few feet below, under that icy blanket, the water remains in its liquid state, protected and stable. And so, a sanctuary is created, a haven for life carved out by the laws of physics. In the dark, still waters beneath the ice, the entire ecosystem of the lake enters a different mode of being. The fish and the amphibians, the insects and the snails, all slow their metabolisms, their own internal fires burning low to conserve energy. Their movements become languid, their need for food diminishes. They retreat from the shallows near the shore, where the water is coldest, and seek refuge in the deepest part of the lake. Here, at the very bottom, the water stays at a constant, life-sustaining 4 degrees Celsius, the temperature at which it is densest and heaviest. It is a world of twilight and patience, a world waiting for the return of the sun, and it is entirely protected by the very cold that seems to threaten it. And so we are left to contemplate the beautiful and profound paradox of ice. We see it as a symbol of stillness, of lifelessness, a force that halts the flow of the world. And yet, here, it is a guardian, a shield born of the biting frost that protects the delicate spark of life from being extinguished. It is a barrier that is also a blanket, a cage that is also a cradle. It shows us that the harshest conditions can sometimes create the most profound forms of protection, that life can find a way to flourish not by fighting the cold, but by using its properties to its own advantage. The strength of this ice is astonishing. This thin, glassy sheet can support the weight of a person, the gentle weight of a whole winter's worth of snow. But what happens when that snow does not melt in the spring? What happens when the winters grow longer and the summers cooler, and the snow begins to accumulate, year after year, century after century? What happens when the gentle weight of a snowflake, multiplied by millennia, begins to press down upon itself, becoming something else entirely? What happens when a protective sheet of ice becomes a river of ice, a force with the patience to grind down mountains and reshape the face of a continent? In the deep, snow-muffled quiet of a northern forest, a great bear curls into a ball in the dark, warm hollow of an ancient tree. Its massive head rests on its paws, and its breath, which in summer comes in powerful warm gusts, has slowed to a faint ghostly mist that barely disturbs the frigid air. The great heart that can pound like a drum during a chase now beats a slow, steady, patient rhythm, just a handful of times each minute. The bear is not dying. It is not even truly sleeping, not in the way that we do. It is waiting. It has surrendered to the season, entering a state of profound stillness, waiting for the sun and the green world to return. This deep slumber is not confined to this single, magnificent creature. The entire forest is breathing with it, in a slow, collective inhalation that will last for all the months of winter. The world has slowed to an almost imperceptible pace. The sap in the maple and birch trees, which runs like a sweet river in the spring, has ceased to flow, retreating deep into the roots. The frantic, vibrant life of the forest floor, the insects, the fungi, the bacteria, has become almost undetectable, a low, dormant hum beneath a thick blanket of snow and frozen earth. A profound quiet has descended, but it is not the quiet of emptiness. It is the quiet of preservation, of energy being carefully, wisely conserved. This remarkable strategy for surviving the long, lean months of cold is a spectrum of deep rest. What the bear is doing is a form of winter lethargy, or torpor. While its heart rate and metabolism slow dramatically, its body temperature only drops by a few degrees. This allows it to awaken relatively quickly if disturbed, a useful adaptation for a large animal that might need to defend its den. But other creatures of the forest enter a state of slumber that is far deeper, a near suspension of life itself. A groundhog, curled in its burrow deep below the frost line, will cool its body from a warm 37 degrees Celsius down to just a few degrees above freezing. Its heart slows to a mere 5 beats per minute. Its breathing becomes so shallow, it is almost non-existent. This is true hibernation, a state so close to death that the line becomes blurred. It is a masterful act of energy conservation, allowing the tiny animal to survive for months on its small stores of body fat. But perhaps the most astonishing winter survivalists are not the warm-blooded mammals, but the cold-blooded amphibians. The humble wood frog, as autumn deepens, will nestle into the leaf litter on the forest floor and begin to produce enormous quantities of glucose, a form of sugar, in its blood. As the first killing frost arrives, the frog allows itself to freeze. Its heart stops beating. Its lungs cease to function. To all appearances, it is a small, solid, frog-shaped ice cube. But it is a miracle of biochemistry. The high concentration of glucose in its vital organs acts as a cryoprotectant, a biological antifreeze. This sugary syrup prevents the formation of sharp, destructive ice crystals inside its cells, which would shred them like microscopic daggers. Instead, the water between the cells is what freezes, encasing them in a protective, solid matrix. The frog can remain in this state of suspended animation for weeks or months, completely frozen, until the warmth of spring thaws its body, restarts its heart, and calls it back to the world of the living. Life finds an endless number of clever ways to wait out the cold. The trees themselves participate in this great retreat. The broadleaf maples and oaks and aspens, which create the glorious canopy of summer, perform a deliberate and beautiful act of surrender. To keep their leaves in winter would be suicide. The dry winter air would pull the moisture from the broad surface of the leaves, and with the ground frozen solid, the tree's roots would be unable to draw up any more water to replace it. And so, the trees let go. They draw back all the valuable nutrients from their leaves, the green chlorophyll, the nitrogen, the phosphorus, storing them safely in their branches and roots. This is what reveals the brilliant yellows, oranges, and reds that were there all along, a final, spectacular flourish before the letting go. A special layer of cells forms at the base of each leaf stem, neatly severing the connection, and the leaf drifts to the ground. The tree seals the wound, hunkers down, and waits, its life force conserved in its wooden heart. In all of these strategies, the bear's torpor, the groundhog's deep hibernation, the frog's frozen stillness, the tree's patient dormancy, there is a profound and gentle wisdom. Our own world so often celebrates constant action, relentless growth, and forward momentum. But the winter forest teaches us a different lesson. It teaches us the wisdom of withdrawal, the power of stillness as a strategy for survival. It shows us that there are times when the most intelligent and effective action is to do nothing at all, to retreat, to conserve our energy, to turn inward, and to simply wait in the quiet dark for the inevitable return of the light. Life, in its infinite variety, has found these ways to wait out the harshest cold. But this raises a different, even more curious question. Can the cold itself, the solid, crystalline world of ice, hold a form of life that does not merely wait, but that actively thrives? A life that calls the frozen world its home, waiting for a different kind of dawn. Deep in the heart of the Antarctic ice sheet, miles from the coast, lies a world of blue, compressed ice, ancient and silent. From the surface, it appears as a sterile, lifeless expanse of white. But if we could shrink ourselves down to the size of a grain of sand and enter this frozen world, we would discover that it is not as solid and unchanging as it seems. Here, In the deep, blue-tinted ice, under pressures that would crush a car into a plate of metal, there are microscopic veins of liquid water, channels thinner than a human hair that snake through the interlocking crystals of the glacier. And within these impossibly small, dark and frigid channels, something moves. Something is alive. We have entered the hidden realm of extremophiles, organisms that live their entire lives in conditions that we would consider utterly uninhabitable. Specifically, these are psychrophiles, a name from the Greek for cold-loving, and they do not merely tolerate the cold, they require it. They are bacteria, archaea, fungi, and algae that have adapted so perfectly to this frozen labyrinth that they would perish if brought into the warmth of our world. This hidden biosphere hints at an even more astonishing secret held by the Antarctic continent. For decades, scientists suspected that beneath the miles-thick ice sheet there might be lakes of liquid water. It seemed impossible, yet the theory held. The immense weight of the ice above 2 or 3 miles of it creates such enormous pressure that it actually lowers the freezing point of water. At the same time, a faint but steady trickle of geothermal heat from the Earth's core warms the base of the ice sheet from below. The combination of these two forces, immense pressure from above and gentle heat from below, creates the conditions for vast, subglacial lakes of permanent liquid water, sealed off from the outside world, some for millions of years. The largest of these, Lake Vostok, is one of the largest lakes on Earth, a body of fresh water the size of Lake Ontario, buried under 2.5 miles of solid ice. For years, scientists have carefully drilled down through the ice, a painstaking process to avoid contaminating this pristine, ancient environment. When they finally broke through and sampled its waters, they found what they were hoping for. A unique ecosystem of microbes, a community of life that has been evolving in total darkness and isolation for eons, surviving on nothing more than the scant chemical nutrients leaching from the rocks below. How can these organisms possibly function in such extreme cold? Their survival depends on a series of beautiful biochemical adaptations. In our own bodies, our cell membranes are made of fats that have a consistency, a bit like soft butter. If they get too cold, they become stiff and hard, and the vital functions of the cell would cease. But the membranes of these psychrophiles are different. They are rich in unsaturated fatty acids, which makes them more fluid, with a consistency closer to that of olive oil. This allows their membranes to remain flexible and functional, even at temperatures near freezing. Their enzymes, the specialized proteins that catalyze all the chemical reactions of life, are also fundamentally different. Our enzymes are tightly wound structures that work best at our warm body temperature. In the cold, they would become too rigid to work. The enzymes of these cold-loving microbes have a much looser, more flexible structure. This allows them to bend and move and carry out their chemical tasks in the deep cold, though it also means they would fall apart and unravel if they were heated up. They are perfectly, exquisitely tailored to their frozen world. These discoveries have fundamentally changed our understanding of the limits of life. We once thought of life as a fragile flame, needing the gentle conditions of warmth, sunlight, and abundant oxygen. But the ice has taught us otherwise. It has shown us that life is a persistent, tenacious, and incredibly adaptable force. It is not a flame but a kind of living crystal, able to flourish in eternal darkness, under crushing pressure, and in profound, perpetual cold. It forces us to reconsider what it means for a place to be habitable. It pushes the boundaries of our imagination. If these dark, cold, hidden realms on our own planet can harbor such unique and resilient ecosystems, then what does that suggest when we turn our gaze upwards to the other frozen worlds we see drifting through the silent darkness of our solar system? What hidden sanctuaries for life might be locked away beneath the icy shells of distant moons? Of course. Here are parts 5 and 6 of the script. Part 5. The glacier's slow song. The mountain is not being worn down by the fleeting violence of wind or rain. It is being unmade, slowly, deliberately, and with unimaginable force, by a river of solid ice. We are standing at its terminal face, the snout of a colossal glacier that spills from the high peaks like a frozen waterfall paused in mid-motion. The air around it is palpably cold, a pocket of ancient winter that persists even under the summer sun. We can hear its voice, a symphony of deep internal groans, as immense stresses shift within its body, punctuated by the sharp, gunshot crack of a new crevasse opening to the sky. We look up at its surface, a chaotic landscape of icy towers and deep vertical shafts that glow with an ethereal, unearthly blue light. This is the light of immense pressure and purity. As snow is compacted over centuries into glacial ice, the tiny air bubbles are squeezed out, creating a substance so dense that when sunlight enters, it absorbs all the colors of the spectrum except for blue, which is scattered back to our eyes. We are looking at the color of time and pressure. We feel its presence not just as a visual spectacle, but as a living entity. An organism of ice with a timescale so vast it defies our human comprehension. The birth of such a titan begins with the gentlest of things, a single snowflake. But in the high, cold places of the world, the snow that falls in winter does not fully melt in the summer. Year after year, new layers of snow bury and compress the old. The delicate, six-sided crystals are crushed together, losing their intricate arms, becoming small, dense granules of ice known as firn. As the centuries pass and the weight of the overlying snow and firn increases, reaching hundreds or even thousands of feet in thickness, the pressure becomes immense. The air is squeezed out from between the granules, and they recrystallize and fuse together, forming a single, solid, interlocking mass of glacial ice. This is no longer the light, airy ice of a frozen pond. It is a new state of matter, a metamorphic rock born of cold and pressure. And once the mass of ice grows large enough, a critical threshold is crossed. It begins to move. Under its own colossal weight, it starts to flow downhill, a river moving in geological slow motion. This movement happens in two beautiful and powerful ways. Deep within the glacier, the pressure is so great that the ice crystals themselves begin to deform. They bend and stretch and slide past one another, allowing the entire mass to flow with the slow, inexorable viscosity of a substance like honey or tar. This process, known as plastic deformation, is the internal creep of the glacier's mighty heart. For many glaciers, especially those in more temperate climates, there is a second mechanism at play. The pressure at the base of the glacier, combined with the friction of its movement over the bedrock, generates a thin layer of meltwater. The entire glacier, weighing billions of tons, can then slide upon this lubricating film, a process called basal slip. It is this combination of internal flow and external sliding that gives the glacier its unstoppable momentum. It is not a static block of ice. It is a dynamic, flowing system, a conveyor belt of frozen time. And as it moves, it sings its slow song of geology, a song of creation through destruction. The glacier is nature's most powerful sculptor. It plucks enormous boulders from the mountainsides, freezing onto them and carrying them effortlessly for miles. The rock and grit embedded in its underbelly act like the teeth of a giant file, scouring and grinding the bedrock beneath, leaving behind long, parallel scratches called striations, the signature of its passing. A V-shaped river valley is transformed into a majestic, steep-sided, U-shaped glacial trough. Two glaciers carving opposite sides of a mountain will leave behind a knife-edge ridge, an arête. Where the ice has finally retreated, it leaves behind a changed world, a landscape of polished rock, deep hollows that will become lakes, and dramatic, breathtaking fjords. Here, in the presence of this slow, immense power, our own sense of time begins to warp. We live in a world of seconds, hours, and days. To a glacier, a human lifetime is but a fleeting moment, a breath. It operates on a scale of centuries and millennia, a deep, patient time that we can barely conceive of. It teaches us that the most profound and lasting changes to the world are often not the quickest or the most violent, but those that are the slowest, the most persistent, and the most patient. This great river of ice is not just a force of erosion, however. It is also a library. As it travels, it consumes and preserves everything in its path, carrying its frozen secrets with it. What stories, then, are written in its ancient, layered heart? What memories of a world before our own are locked away in its slow, crystalline journey? Imagine for a moment that you could hold in your gloved hands a perfect cylinder of ice, drilled from the deepest parts of Greenland or Antarctica. It is cold and translucent, and as you look closely, you can see, trapped within it, like tiny jewels, a constellation of small, silvery bubbles. And then you are told that the air inside those bubbles is not the air of our time. It is the air that was breathed by mammoths, the air that filled the sky during the time of the Roman Empire, the air from before the first stirrings of the Industrial Revolution. You are not just holding a piece of ice. You are holding a piece of the ancient atmosphere itself, a tangible, pristine message from the deep past. This is the incredible reality of the science of ice cores. We are in a cold laboratory, a vast, refrigerated archive where these treasures are stored. The temperature is kept at a steady -30 degrees Celsius. All around us, long tubes of ice, each one about a meter long, are laid out on tables. Each core is a timeline, a book whose pages are layers of ice, stretching back hundreds of thousands of years into the history of our planet. In the great, frozen plateaus of Antarctica and Greenland, the snow rarely, if ever, melts. Each year, a new layer of snowfall buries the last, and as we saw with the birth of a glacier, this snow is gradually compressed into ice. Crucially, as the granular snow transforms into solid ice, it traps small pockets of the surrounding air. And so, the ice sheet becomes a perfectly ordered archive. The deeper you drill, the older the ice, and the older the air trapped within it. Scientists can drill down for more than 2 miles, pulling up cores that provide a continuous, year-by-year record of the Earth's climate, stretching back over 800,000 years. By examining the ice itself, we can learn about the temperature of the past. The key lies in the water molecules. Water, H2O, is mostly made of a light version, or isotope, of oxygen called oxygen-16. But a tiny fraction of water contains a slightly heavier isotope, oxygen-18. Water containing this heavier isotope is more difficult for the sun's energy to evaporate from the ocean's surface, and it is more likely to condense and fall as rain before it reaches the frigid poles. This means that during colder periods in Earth's history, the air that travels to the poles is even more depleted of the heavy oxygen-18 than usual. Therefore, the snow that falls and becomes ice during an ice age has a measurably lower ratio of oxygen-18 to oxygen-16. By analyzing this isotopic ratio in each layer of the ice, scientists can reconstruct a stunningly precise history of global temperature. The ice core is a natural thermometer, a paleothermometer of astonishing accuracy. But the real magic lies in those tiny, trapped bubbles. They are a direct sample, a fossil of the ancient air. In the sterile cold of the lab, scientists can carefully cut a piece of the core, place it in a vacuum chamber, and gently break it open, releasing the ancient atmosphere to be analyzed by sensitive instruments. For the first time, we could directly measure the composition of the atmosphere from the distant past. We could find out exactly how much carbon dioxide, or CO2, and methane, or CH4, existed in the air during the last ice age, or during the warm periods in between. And when they laid the data from the air bubbles next to the temperature data from the water isotopes, they saw a relationship of breathtaking clarity. The two graphs rose and fell in a near-perfect, synchronized dance. When carbon dioxide and methane levels were high, the planet was warm. When they were low, the planet was plunged into an ice age. It was the definitive physical proof of the powerful link between greenhouse gases and the Earth's climate, written not in computer models or theories, but in the planet's own frozen diary. We are left with a feeling of profound connection and humility. The Earth, it seems, keeps its own meticulous records. The past is not lost or forgotten. It is simply frozen, preserved in an immaculate library of ice, waiting for us to develop the tools and the curiosity to learn how to read its silent language. These crystalline pages tell us a story of a planet that breathes, a world of dynamic and dramatic change, of vast cycles of cold and warmth, of great advances and retreats of the ice sheets. This clear, recorded history begs a vital question. What is the grand, cosmic rhythm that the Earth is dancing to? What celestial clockwork is pulling the levers that bring about these immense and powerful ages of ice? The great ice ages that have so profoundly shaped our planet, the vast continental glaciers that have advanced and retreated, sculpting mountains and carving valleys, are not random acts of a chaotic climate. They are not accidents. They are the result of a slow, majestic, and entirely predictable wobble in the Earth's celestial dance. They are the ticking of a cosmic clock, whose gears are the orbits of planets, and whose pendulum is the tilt of our world. To understand this, we must pull our perspective away from the surface of the Earth, away from the familiar landscapes of rock and water and air, and travel out into the silent, black emptiness of space. From here, we can watch our planet as a whole, a beautiful blue and white marble in its long, looping journey around the sun. We see its gentle tilt, the elegant angle that gives us our seasons. We see its slightly imperfect orbit, not quite a circle. And if we could watch for not just a single year, but for 100,000 years, we would see that these simple orbital characteristics are not fixed. They are in a constant, slow, and graceful state of flux, a planetary ballet choreographed by the gravitational pull of our celestial neighbours. This grand rhythm is described by what are known as the Milankovitch cycles, named for the Serbian scientist Milutin Milankovic, who first calculated their profound influence on our climate. There are three main movements in this cosmic dance. The first is eccentricity, which is simply a measure of how much our orbit deviates from a perfect circle. Over a long and steady cycle of about 100,000 years, the Earth's orbit slowly stretches from being nearly circular to being more elliptical or oval-shaped, and then back again. This may seem like a small change, but it alters the total amount of solar radiation our planet receives over the course of a year. When the orbit is more elliptical, the difference in the sun's energy between our closest and farthest approach is much greater, which can have a significant effect on the climate. The second movement is a change in our planet's axial tilt, or obliquity. We know that the Earth is tilted on its axis at about 23.5 degrees, and this tilt is the reason for our seasons. But this angle is not constant. Over a cycle of about 41,000 years, the axis slowly rocks back and forth, varying between a tilt of about 22.1 degrees and 24.5 degrees. When the tilt is greater, the seasons are more extreme, hotter summers and colder winters. When the tilt is smaller, the seasons are much milder. And a mild summer is the most important ingredient for building an ice age. A brutally cold winter can create a lot of snow, but a hot summer will melt it all away. A cool, gentle summer, however, allows some of the winter snow to survive. And when snow can survive the summer, it begins to accumulate, year after year, starting the process of building a glacier. The third and final movement is called precession. This is the slow wobble of the Earth's axis, very much like the wobble of a spinning top as it begins to slow down. This wobble takes about 26,000 years to complete one full circle, and it changes the timing of the seasons. It determines which stars are our pole stars, and critically, it determines whether a hemisphere's summer solstice occurs when the Earth is at its closest point to the Sun in its orbit, or at its farthest point. These three cycles, the stretching of the orbit, the rocking of the axis, and the wobble of its spin, are all happening at the same time, on different schedules. They overlap and interfere with each other, sometimes cancelling each other out, and sometimes reinforcing one another to create a period of profound climatic change. When the cycles align just right, creating a long period of cool northern summers, the great ice sheets begin their slow, inexorable advance. In this grand, cosmic perspective, we are humbled. We learn that the climate of our world is not an isolated system. It is written not just in our oceans and atmosphere, but in the gravitational tug of distant Jupiter and Saturn, whose immense gravity is what perturbs our orbit over these long eons. We are intimately connected to the mechanics of the solar system. We are living within the workings of a great and ancient clock. The Earth, however, is not the only world in our solar system that is governed by the physics of ice. Far from the sun's warmth, in the outer darkness, there are moons that are almost entirely frozen. But is their ice as still and silent as the ice of our own world's glaciers? Or does it hide a secret far more profound? Beneath a solid shell of ice, harder than granite and perhaps 100 times thicker than any glacier on Earth, there is an ocean. It is an ocean of liquid salt water, vast and deep and utterly dark, and it does not exist on our planet. It exists on a moon of Jupiter. We journey now, out past the orbit of Mars, past the asteroid belt, to the realm of the gas giants. Here, circling the colossal planet Jupiter, is a collection of fascinating worlds. One of them, named Europa, shines with a brilliant white light. As we draw closer, we see its surface is not a blank sheet of white, but a complex and fractured world, covered in a web of long, linear cracks and reddish-brown ridges that stretch for thousands of miles. It is a world that has been broken and healed many times. It is the face of a world with a secret, and that secret is the vast, hidden ocean that we now journey to in our imagination. We descend through the thick, frozen crust. Miles and miles of solid ice pass by, a journey through a substance so cold and under so much pressure it would be as strong as solid rock. And then, after a descent of perhaps 10 or 20 miles, we break through. We are floating now in a darkness more complete than any on Earth, in a silence more profound than any we have ever known. We are in the subglacial ocean of Europa. How can such a place exist? Europa is more than 5 times farther from the Sun than Earth is. Its surface temperature is a numbing minus 160 degrees Celsius. By all rights, it should be frozen solid to its very core. The answer lies not in the warmth of the Sun, but in the immense, overwhelming power of Jupiter itself. Europa is locked in a constant gravitational tug-of-war. As it orbits the giant planet, the immense gravity of Jupiter pulls on it, deforming its shape. And because its orbit is not perfectly circular, this tidal pull is not constant. It varies, stretching and squeezing the little moon relentlessly. This process is called tidal heating. You can feel a similar effect by taking a metal paperclip and bending it back and forth rapidly in your hands. The metal will quickly grow warm from the internal friction. The same thing is happening to Europa on a planetary scale. The constant flexing of its interior generates enormous amounts of heat, enough to maintain a vast body of water in its liquid state, protected beneath the insulating shell of the icy crust. Scientists are remarkably confident that this ocean exists, even though we have never seen it directly. The evidence is compelling and comes from several sources. The fractured and chaotic terrain of the surface, with huge rafts of ice that look like they have broken apart, drifted, and frozen back into place, strongly suggests they are floating on a liquid layer below. Furthermore, spacecraft have detected that Europa has a weak magnetic field. This field is not generated by the Moon itself, but is induced, or created, by its passage through Jupiter's powerful magnetic field. For this to happen, Europa must contain a layer of some electrically conductive material, and a global ocean of salty water fits this observation perfectly. And perhaps most excitingly, the Hubble Space Telescope and other observatories have detected tantalizing evidence of what appear to be huge plumes of water vapor erupting from cracks in Europa's southern hemisphere, geysers that shoot hundreds of miles into space, providing a potential glimpse of the ocean material from below. This hidden, tidally heated ocean makes Europa one of the most promising places in the entire solar system to search for extraterrestrial life. As we currently understand it, life requires 3 key ingredients: liquid water, a source of energy, and the right chemical elements. Europa appears to have all 3. The liquid water is there in abundance. The energy comes from tidal heating. And the necessary chemical elements are likely supplied by the rocky seafloor, which may be dotted with hydrothermal vents, just like the volcanic vents on Earth's own ocean floors. Here on Earth, these vents, spewing hot, mineral-rich water from the planet's interior, support entire ecosystems of bizarre and wonderful creatures that thrive in total darkness, a form of life that runs on chemistry instead of sunlight. Could something similar be happening right now, in the silent, dark, hidden ocean of Europa? It is a profound and tantalizing question. It makes us reflect on the nature of discovery. Perhaps the greatest secrets of the universe, the most profound answers we seek, are not out in the open, shining brightly for all to see. Perhaps they are locked away, waiting for us, beneath the most impenetrable, forbidding, and frozen of surfaces. These icy moons hold oceans. But other frozen bodies wander the solar system, not as worlds, but as messengers, carrying the very building blocks that may have made our own world possible. What are these ghostly visitors, these dirty snowballs that we call comets? In the deep, velvet darkness of the night sky, far from the obscuring glow of city lights, a new star sometimes appears where none was before. At first, it is just a faint, ethereal smudge of light, a soft, hazy patch against the crisp backdrop of the constellations. But night after night, it grows brighter, and a long, diaphanous tail begins to unfurl behind it, a ghostly banner stretching across the heavens. This is a visitor. It is a traveller from the outermost, coldest edge of our solar system, a ball of ancient ice and dust that has been wandering the dark for billions of years, and has now, finally, fallen back into the warm heart of our neighbourhood. This is a comet, a messenger from the time of our creation. Let us journey alongside it. In the deep space beyond the orbit of Neptune, our comet is just a dark, lumpy, and unassuming object, perhaps a few miles across. It is a nucleus of what scientists call an icy dirt ball, a fragile, porous mixture of frozen water, frozen gases like carbon dioxide, methane, and ammonia, all bound together with particles of rock and dust. For eons, it has drifted in this inert state, a preserved relic from the dawn of the solar system, 4.6 billion years ago. It is a time capsule, holding the pristine, primordial material from which the Earth and all the other planets were formed. But now, its long, lazy orbit is bringing it closer to the Sun. As it crosses the orbit of Jupiter, the Sun's warmth begins to touch its surface for the first time in millennia. The ancient ices, which were stable in the deep cold, can no longer remain solid. They begin to sublimate, turning directly from a solid into a gas, just like dry ice does on Earth. Jets of this gas, mixed with dust, erupt violently from cracks and fissures in the dark nucleus, creating a vast, glowing cloud around it. This luminous atmosphere is called the coma, and it can grow to be larger than a planet. The comet has awakened. As it continues its fall toward the Sun, this glowing head begins to grow its spectacular tails, and there are not one, but two distinct tails, each formed by a different process. The first is the dust tail. It is made of the larger, heavier particles of dust and grit that were mixed in with the ice. These particles are pushed away from the comet's nucleus by the gentle but incessant pressure of sunlight itself. Photons of light, though they have no mass, carry momentum, and this constant stream of light acts like a very faint wind, pushing the dust particles away. Because the dust is relatively heavy, it lags behind in the comet's orbit, forming a broad, gently curved tail that often shines with a soft, yellowish-white light, reflecting the sun. The second tail is the ion tail, or the plasma tail. It is made of the gases that have vaporized from the nucleus. As these gas molecules drift away from the comet, they are struck by the sun's powerful ultraviolet radiation, which is energetic enough to strip electrons from them, giving them a positive charge. They become ions. These charged particles are then grabbed by the solar wind, a fast-moving stream of charged particles that is constantly flowing outwards from the sun, and are blown straight back, away from the sun, with tremendous speed. This ion tail is much thinner and straighter than the dust tail, and it often glows with a brilliant, eerie blue light as the ions are energized by the solar wind. It acts like a celestial weather vane, always pointing directly away from the sun, no matter which way the comet itself is traveling. These beautiful, ghostly visitors may have played a crucial role in our own existence. In the early days of the solar system, the young Earth was a hot, dry, and barren rock. The leading theory for where our vast oceans came from is that for millions of years, the Earth was bombarded by countless comets and asteroids from the outer solar system, each one delivering its cargo of frozen water. These ancient impacts may have filled our oceans and, what is more, these comets are also rich in complex organic molecules, the carbon-based building blocks of life. These icy messengers may have delivered not just the water for life, but the very seeds from which life could begin. And so, we look up at a comet not just as an astronomical curiosity, but as a connection to our own deepest origins. The water that flows in our rivers, the water that makes up more than half of our own bodies, may have once been locked in the frozen heart of a comet that travelled for billions of years through the interstellar void. We are made, in a very real sense, of the stuff of stars and of ancient, wandering ice. Comets are messengers from the distant past of our solar system. But what does the ice on a much closer world, the planet Mars, tell us about the lost history of that single, rust-coloured planet? The polar caps of Mars, gleaming white against the planet's ochre deserts, are not just static fields of ice. They are vast, layered chronicles of a world that was once blue. They are the pale ghosts of a warmer, wetter past, a history written in frozen water and frozen air. Let us drift now in orbit above the red planet, looking down upon its northern pole. It is a stunning sight, a vast swirl of white ice and dark red dust, etched with enormous spiral troughs that make it look like a celestial pinwheel, a hurricane frozen in time. These canyons are carved not by water, but by a persistent wind that spirals outwards from the pole, slowly sublimating the ice and shaping it over millions of years. As the Martian seasons change, we can watch a remarkable transformation. In winter, a bright, expansive layer of new frost appears, stretching far down into the mid-latitudes. This is not water ice. It is frozen carbon dioxide, dry ice, condensing out of the thin Martian atmosphere as temperatures plummet. Then, as spring arrives, this seasonal cap begins to retreat, not by melting, but by sublimating directly back into a gas, revealing the permanent and much thicker water ice cap that lies beneath. This permanent northern cap alone holds a vast amount of water, more than the Greenland ice sheet on Earth. But this is just the most visible of Mars's frozen reservoirs. The true story of Martian water lies hidden, buried beneath the red dust. For years, orbiters equipped with ground-penetrating radar have been mapping the planet's subsurface, and they have found something astonishing. In the planet's mid-latitudes, far from the poles, there are massive glaciers of pure water ice, hundreds, even thousands of feet thick, buried and preserved beneath a protective layer of dust and rock. These are not small pockets of frost. They are colossal bodies of ice, remnants from a past ice age when Mars's axial tilt was more extreme, causing snow to fall and accumulate not at the poles, but closer to the equator. If you add up all the ice in the polar caps, and all of these buried glaciers, and all of the water locked away as permafrost in the soil, there is enough frozen water on Mars to cover the entire planet in a global ocean more than 100 feet deep. The water is still there. It is just in a deep freeze. And we know, with near certainty, that this water once flowed freely. All across the surface of Mars, we see the ghosts of a blue planet. Rovers crawling across the rusty plains have found winding, sinuous channels that are unmistakably dried-up riverbeds. Orbiters have photographed vast, fan-shaped deltas, like the one in Jezero crater, where powerful rivers once emptied into deep, calm lakes, depositing layers of sediment just as the Mississippi River does in the Gulf of Mexico today. We have seen evidence of catastrophic outflow channels, carved in a matter of weeks by biblical-scale floods that burst from beneath the surface. And the chemistry confirms it. We have found minerals like clays and sulfates, which, on Earth, can only form in the presence of standing liquid water over long periods of time. The evidence is overwhelming. Mars was once a world with a thicker atmosphere, a warmer climate, and on its surface, flowing rivers, deep lakes, and perhaps even a shallow ocean in its northern hemisphere. Contemplating this history brings a sense of profound and melancholy wonder. Mars is a planetary cautionary tale, a world that lost its water. Over billions of years, its thin gravity and the loss of its protective magnetic field allowed the solar wind to strip away its atmosphere, causing the pressure to drop and the planet to cool. The water that once flowed either evaporated into space or retreated into the ground, freezing into the icy ghosts that we see today. The red planet is a reminder of how precious and perhaps how fragile a world's climate can be. It reminds us that the ability to hold a warm, flowing, life-giving ocean on a planet's surface is a delicate and perhaps temporary gift. We have explored the ice that preserves the history of planets. But now, let us turn our journey inward. How does our own mind, our own consciousness, perceive the sensation of cold? And how does that fundamental physical feeling reach in and shape the landscape of our inner, emotional world? Why does the phrase "a cold heart" mean something more than just a low temperature? Why do we speak of a frosty reception or giving someone the cold shoulder? The sensation of cold, it seems, reaches far deeper than our skin. It touches our emotions, our language, and our very sense of connection to one another. It is a physical reality that has profoundly shaped our inner world. Let us retreat for a moment to a quiet room on a winter's day. We are sitting by a large window, and on the glass, intricate, fern-like patterns of frost are blooming, tiny crystalline forests spreading across the pane. The world outside is hushed and white under a blanket of snow. We can feel the subtle chill that radiates from the window, and we notice a corresponding quietness in our own thoughts. There is a natural tendency to turn inward, a desire for stillness and contemplation that seems to mirror the dormant world outside. This deep connection between the physical sensation of cold and our psychological state is not just poetry, it is a fundamental aspect of our biology and our evolution. When the cold air touches your skin, an army of microscopic sensors called thermoreceptors springs into action. These specialized nerve endings are our body's thermometers, constantly monitoring our thermal environment. When they detect a drop in temperature, they send a rapid-fire volley of electrical signals up the spinal cord to the brain. The message arrives at a deep, ancient part of the brain called the hypothalamus, which acts as our body's central thermostat. The hypothalamus immediately orchestrates a series of involuntary responses designed to protect our vital core temperature. It triggers shivering the rapid, fluttering contraction of our muscles, a desperate attempt to generate heat through movement. At the same time, it initiates vasoconstriction, the narrowing of the blood vessels in our skin, hands, and feet. This is the body making a difficult but wise decision. It reduces blood flow to the extremities, sacrificing the warmth of our limbs to pull our precious, warm blood inward, keeping our vital organs like the heart, lungs, and brain safe and functional. This is the purely physical response. But the brain does not process this information in a vacuum. The signals of cold are cross-referenced with our emotional centers, with our deepest memories and instincts. For our distant ancestors, cold was not a matter of comfort. It was a matter of survival. Cold meant the scarcity of food, the danger of frostbite, the threat of freezing to death in the long, dark night. It was a time for caution, for conserving energy, for huddling together for warmth. Because of this deep evolutionary history, the sensation of cold has become psychologically associated with concepts of stillness, silence, solitude, danger, and even death. Warmth, in contrast, is tied to everything that counters those threats. Warmth is the safety of the fire, the comfort of a mother's embrace, the abundance of summer, the life-giving energy of the sun. It is safety, connection, and vitality. This is why our language is so rich with these thermal metaphors. A warm welcome feels safe and inviting. A cold-hearted person is seen as unemotional and potentially dangerous. The link is written into the very structure of our thought. Even more fascinating is the discovery that this link is not just metaphorical. Recent science has revealed a literal, neurological overlap between physical temperature and our feelings of social connection, a concept sometimes called social thermoregulation. In one remarkable study, people were asked to recall a memory of a time they felt either socially included or socially excluded. Afterward, they were asked to estimate the temperature of the room they were in. Those who had just relived a memory of social rejection of being given the cold shoulder consistently estimated the room to be significantly colder than those who had remembered a time of acceptance and belonging. The feeling of being left out in the cold is, it seems, a physical reality. In another experiment, participants holding a cup of hot coffee were more likely to judge a stranger's personality as being warmer, more generous, and more trustworthy than participants who were holding a cup of iced coffee. Our brain, it seems, does not draw a hard line between physical warmth and social warmth. They are processed in related neural pathways. This shows us how porous the boundary is between our inner and outer worlds. Our most fundamental physical sensations are not just objective data about the environment. They are woven into the very fabric of our emotional lives, shaping how we feel, how we think, and how we connect with each other. If our minds can feel frozen by a moment of exclusion, what happens when we attempt to use this profound cold to cheat time itself, to literally freeze not just a feeling, but an entire life? Deep inside a frozen mountain, halfway between mainland Norway and the North Pole, lies a modern wonder of the world. Behind layers of solid rock and ancient permafrost, protected by the planet's own natural freezer, lies a library of life. It is a vault, a sanctuary, an ark. It holds the key to rebuilding our agricultural world. This is the Svalbard Global Seed Vault, and it is a testament to human foresight, a profound act of hope in the face of an uncertain future. Our journey takes us to a remote, starkly beautiful island in the Arctic Ocean, a land of glaciers, polar bears, and the midnight sun. Here, jutting out from the side of a snow-covered mountain, is a single, sharp wedge of concrete and illuminated glass. The entrance to the vault, it looks like a portal to another world. And in a way, it is. We move through the long, steel-lined tunnel that slopes down into the mountain's heart. The air grows colder with every step, and the rock walls become coated in a thick layer of ice crystals that glitter in the lamplight. Finally, we arrive at a series of heavy, airtight doors. We pass through them into the main vault chambers. Here, in the deep, humming silence and the profound cold, are rows upon rows of tall metal shelves. And on these shelves are not books, but millions upon millions of small, sealed foil packages, each one containing a precious cargo, the seeds of our planet's food crops. The purpose of the Svalbard Vault is simple and profound. It is not a normal seed bank for everyday use. It is a fail-safe, a global backup copy of the world's agricultural biodiversity. All over the world, there are hundreds of national and regional gene banks that store seeds of the crops important to their area. But these banks are vulnerable. They can be destroyed by war, by natural disasters like floods or earthquakes, or simply by mismanagement or lack of funding. The Svalbard Vault is the ultimate insurance policy. Countries and institutions can deposit duplicate copies of their seeds here for safe, long-term storage, free of charge. Should the worst happen and a local collection be lost, its contents can be retrieved from this Arctic sanctuary and regenerated. This is not just a theoretical possibility. The vault has already served its purpose. A vital seed bank in Syria was forced to close due to the civil war, but because its curators had wisely sent duplicates of their unique collection of wheat, barley, and chickpeas to Svalbard, they were able to withdraw them, regrow them in a safe location, and continue their crucial research. The science that makes this possible is a masterful application of cryopreservation, the art of preserving life with cold. The entire process is designed to bring the seeds into a state of suspended animation. First, and most critically, the seeds are carefully dried until their moisture content is reduced to around 5%. Then, they are sealed in custom-made 3-ply foil packages that keep out any remaining moisture. These packages are then placed in boxes and stored in the vaults, which are kept at a constant, frigid temperature of -18 degrees Celsius, maintained by the natural permafrost of the mountain and supplemented by artificial cooling systems. This combination of being intensely dry and intensely cold is what works the magic. The extreme cold slows down all metabolic activity within the seed cells to an almost complete standstill. The aging process, for all practical purposes, stops. The drying process is the key to preventing damage. As we learned from the wood frog, the great danger in freezing living tissue is the formation of sharp ice crystals inside the cells, which would puncture the delicate cell walls and kill the organism. By removing almost all of the water before freezing, there simply isn't enough left to form these destructive internal crystals. The tiny amount of water that remains can freeze in a vitrified, or glass-like, state that does not damage the cellular machinery. In this state of deep, dry cold, many seeds can remain viable for hundreds, or even thousands of years, holding their spark of life in perfect stillness, waiting for the day they might be called upon to grow again. This vault is one of the most optimistic projects humanity has ever undertaken. It is a gift to the future, a message of stewardship and responsibility. It is a quiet, humble, and deeply moving expression of our belief in the resilience of life and in our duty to protect it. We freeze these seeds to safeguard the future of our world. But what happens when nature's own long-term freezer, the ancient permafrost of the north, begins to thaw and awakens a form of life that has been sleeping for tens of thousands of years? From the melting edge of a riverbank in the vast empty plains of Siberia, a shape emerges that has not been seen by the sun in 40,000 years. It is the head of a woolly mammoth, its long curved tusks pointing to the sky, its coarse reddish-brown hair still clinging to its frozen skin. It is a ghost from the Pleistocene, an emissary from the last ice age, returned to our world not by magic, but by the simple act of thawing. This is the new reality of the Arctic. We are standing now on the tundra, a landscape that for millennia was defined by its solid permanence. The ground underfoot, known as permafrost, was as hard and reliable as rock. But today, the ground is soft. It is boggy and unstable, pockmarked with pools of meltwater that glitter under a sun that feels unnervingly warm. And with the thaw comes a smell. It is a deep, rich, and ancient smell, the earthy scent of decomposition, as layers of grass, moss, roots, and animal remains, frozen in time since before the dawn of human civilization, are exposed to the air and begin to rot for the very first time. Permafrost is defined as any ground, be it soil, rock, or sediment, that has remained continuously at or below 0 degrees Celsius for at least 2 consecutive years. It is a vast subterranean continent of ice, covering nearly a quarter of the land surface in the northern hemisphere. For thousands of years, it has acted as a kind of planetary freezer. The top layer, called the active layer, has always thawed for a few months in the brief Arctic summer, allowing a shallow blanket of hardy vegetation to grow. But beneath this, the deep permafrost remained solidly, reliably frozen. Now, as the Arctic warms faster than anywhere else on Earth, this active layer is growing deeper, and the ancient permafrost below is beginning to thaw and to awaken. And as it awakens, it releases its long-held secrets. The perfectly preserved mammoth is just the most spectacular example. Scientists drilling into the permafrost have discovered a microscopic world of life, frozen in a state of suspended animation for unimaginable lengths of time, and they have brought it back to life. In laboratories, they have successfully revived giant, 30,000-year-old viruses, which, while harmless to humans, were still able to infect amoebas after their long slumber. They have thawed out 42,000-year-old nematode worms, which, within weeks, began to move and to eat again. Perhaps most poetically, scientists discovered the fossilized burrow of an Ice Age ground squirrel, which contained, among other things, the fruit tissue of an ancient flower. From this 32,000-year-old piece of tissue, they were able to regenerate a living, flowering plant, its delicate white petals opening to a world utterly transformed from the one its parent knew. But this thawing world is not just a scientific treasure trove. It is also a potential time bomb. For hundreds of thousands of years, the permafrost has been accumulating and storing a vast amount of carbon, the frozen, undecomposed remains of countless generations of plants and animals. The total amount of carbon locked away in the permafrost is estimated to be twice as much as is currently in our entire atmosphere. As long as it remained frozen, this carbon was stable and harmless. But as the permafrost thaws, this organic matter becomes a feast for newly awakened microbes. As these bacteria and fungi consume the ancient carbon, they release waste products into the air. Carbon dioxide, and in waterlogged areas without oxygen, vast quantities of methane. Methane is a greenhouse gas more than 25 times as potent as carbon dioxide at trapping heat in the atmosphere. The thawing of the permafrost thus creates a dangerous positive feedback loop. The warming thaws the permafrost, which releases greenhouse gases, which causes even more warming, which thaws even more permafrost. We are left with a profound and unsettling paradox. The Great Thaw reveals the breathtaking secrets of the past, offering us a perfect flower from a lost world. Yet at the same time, It unleashes the dangers of that past, threatening to accelerate our journey into a warmer and more uncertain future. The past, it seems, is not dead. It is merely frozen, and its awakening will have consequences for us all. The permafrost holds the carbon of ancient life, but far from the tundra, in the crushing darkness of the deep sea, a completely different kind of ice has formed, trapping not the carbon of the past, but a potent fuel for the present. Imagine holding in your hands a piece of ice, pulled from the crushing darkness of the ocean floor. It is cold to the touch, white and crystalline. But if you were to bring a lit match to its surface, something impossible would happen. The ice itself would catch fire, burning with a steady, dancing flame as it melts into a puddle of water. This is methane clathrate, a substance often called burning ice. It is one of the strangest and most abundant materials on our planet, a bizarre form of ice that holds a ghost within its crystal cage. To find it, we must journey down, far below the sunlit surface of the ocean, into the realm of the abyss. In a deep-sea submersible, we descend through the twilight zone and into a world of absolute blackness and immense pressure. The water outside our viewport is near freezing. Our powerful lights cut through the darkness, illuminating the soft, silty expanse of the seafloor. And there, we see it. Growing from the sediment like strange, white coral are large deposits of this uncanny substance. Our submersible's robotic arm reaches out and carefully breaks off a piece. As we begin our ascent, a curious thing happens. The solid, ice-like chunk begins to fizz violently, releasing a torrent of bubbles, dissolving into nothing as it rises. It is a substance that can only exist in its native home of high pressure and low temperature. This burning ice is not, in a chemical sense, true ice. It is a solid crystalline compound in which water molecules, under the right conditions, form a rigid, cage-like lattice. This cage structure, called a clathrate, then physically traps other, smaller molecules inside. In this case, the prisoner in the cage of frozen water is methane, the primary component of natural gas. It forms naturally and in enormous quantities in the sediments of the deep ocean floor and in terrestrial permafrost, wherever the necessary conditions of high pressure and low temperature allow the water cages to form and trap the methane gas that is constantly seeping up from the Earth's interior. This bizarre substance is of immense interest because of the sheer quantity that exists. The total amount of carbon locked away in the world's methane clathrate deposits is staggering, conservatively estimated to be twice the amount of carbon found in all of the planet's other known fossil fuels, all the coal, oil, and conventional natural gas combined. It represents one of the largest reservoirs of carbon on the planet, a potential energy source of unimaginable scale. But it is also a source of profound environmental risk. The stability of these vast clathrate deposits is delicately balanced, dependent on that narrow window of cold temperatures and high pressures. If the deep oceans begin to warm as a result of global climate change, these solid deposits could begin to destabilize and melt. The cages of water would break apart, releasing their trapped methane gas directly into the ocean. If this release were slow, the methane might be consumed by ocean bacteria or dissolve. But if the warming were to trigger a more rapid, large-scale dissociation, vast plumes of methane gas could bubble up and reach the atmosphere. This is the scenario outlined in the clathrate gun hypothesis. It suggests that a rapid release of methane from the seafloor could trigger a runaway feedback loop of abrupt and catastrophic climate change as the powerful greenhouse gas floods the atmosphere and rapidly drives temperatures even higher. We do not know how likely such an event is, or how close we might be to such a tipping point. And so, we are left to contemplate the hidden power of our planet. In the silent, dark, and seemingly empty plains of the abyss, there are forces and substances locked away that we are only just beginning to comprehend. We see that our world is a system of delicate balances, and that our actions on the surface, the warming of our atmosphere, could have unforeseen consequences, disturbing sleeping giants in the deep. The Earth holds its own strange and fiery forms of ice. But what happens when we, in our own quest for knowledge and longevity, try to harness the power of profound cold to stop time itself, to freeze not just a gas, but the very fabric of a human life? In a quiet, climate-controlled room within a tall, gleaming stainless steel vessel that looks like a giant thermos flask. A human being is waiting. They are not alive in the way that we understand it. Their heart is still. Their lungs do not breathe. But they are not truly dead either. Their body is held in a state of perfect, crystalline stillness, at a temperature of -196 degrees Celsius, bathed in liquid nitrogen. They are waiting for a future that may never come, for a technology that does not yet exist. This is the strange, hopeful, and profoundly controversial world of cryonics. We are in a facility dedicated to this very practice. The air is clean and sterile, humming with the quiet, steady sound of monitoring equipment and cooling systems. Frost coats the pipes and valves on the large, insulated containers, which are called dewars. Inside, each one is a human body, or in some cases, just the brain, held in a state that is meant to bridge the gap between a life that has ended and a life that might, one day, be resumed. It is humanity's most ambitious attempt to use the power of cold to stop the river of time. The central challenge of this endeavor is the very substance we have been exploring: ice. We know that when water freezes, it forms sharp, destructive crystals. To simply freeze a human body would be to destroy it on a cellular level, turning it into a shattered ruin. And so, modern cryonics does not freeze. It vitrifies. The process begins at the moment of legal death. A medical team works to restore circulation and oxygenation to the brain, and then, the patient's blood is slowly replaced with a sophisticated cocktail of chemicals called cryoprotectants. These are medical-grade antifreezes that permeate every cell of the body. Then, over several days, the body is cooled down. Because of the cryoprotectants, the water within the cells does not crystallize. Instead, as the temperature drops, it becomes more and more viscous, like honey in winter, until it seamlessly transitions into a solid state without any crystal formation at all. It becomes an amorphous solid, a kind of biological glass. The goal is to preserve the delicate, intricate architecture of the body, and most importantly, the brain, in a stable, unchanging, glass-like state. The entire practice is built upon a central hypothesis, a great and unproven bet. This is the idea that our identity, our memories, our personality, our consciousness, the very essence of who we are, is stored in the physical structure and chemical patterns of the brain's trillions of neural connections. If that structure, the connectome, can be preserved with sufficient fidelity, then, in theory, a vastly advanced future technology might be able to scan, repair, and revive that brain. They would need to be able to reverse the vitrification, fix any damage caused by the original illness or the preservation process itself, and reanimate the cells. It is a hope placed in a future that is, for us, pure science fiction. But this is not just a technical problem. It opens a series of deep and poignant philosophical questions. If a person were revived, hundreds or even thousands of years from now, would they still be you? Is the sum of your memories a complete definition of yourself? Or is an unbroken stream of consciousness essential to your identity? What would it mean to awaken in a world where every person you knew, every piece of art you loved, every institution you understood, has long since turned to dust? We are left to meditate on the nature of time and identity. We experience our lives as a river, a constant process of flow and change, of becoming and unbecoming. Cryonics is a profound attempt to build a dam in that river, to stop the flow, to take a single, static snapshot of a life and preserve it in glass. But in doing so, are we truly preserving a person, or are we preserving a perfect but lifeless echo? A beautiful ice sculpture of a soul, waiting for a dawn that may never break. We dream of stopping time with this profound cold, but what is the absolute limit of cold itself? What happens when you try to stop the motion of everything, everywhere in the universe? There is a temperature so cold that it is the very definition of coldness itself. A point on the scale where the universe runs out of numbers. A state of such profound stillness that all the frantic, chaotic motion that defines our warm and living world almost holds its breath. This is absolute zero, the ultimate and final frontier of cold. We travel now not to a distant planet or a deep ocean, but to a quiet laboratory, a clean, still room filled with some of the most sophisticated machinery ever created by human hands. Gleaming, stainless steel vacuum chambers are surrounded by a web of lasers, mirrors, and optical fibers, all connected by a tangle of wires to racks of precise electronic equipment. There is the faint, low hum of powerful electromagnets and vacuum pumps. Here, in this controlled and pristine environment, physicists are on a quest to get as close as is physically possible to that final, absolute state of cold. First, we must understand what we mean by temperature. The heat we feel is simply a measure of the kinetic energy of atoms and molecules. In the air around you, molecules of nitrogen and oxygen are moving at hundreds of miles per hour, constantly vibrating, rotating, and crashing into one another. The faster they move, the hotter the substance is. Cold, then, is simply the slowing of this motion. Absolute zero, which is defined as zero on the Kelvin scale, equivalent to minus 273.15 degrees Celsius, is the theoretical point at which all of this classical motion ceases. It is the state of minimum possible energy. However, the third law of thermodynamics, one of the fundamental rules of our universe, states that while you can get tantalizingly, infinitesimally close to absolute zero, you can never, ever actually reach it. It is an asymptote, a limit that can be approached but never touched. To get close to this limit, scientists employ a series of ingenious techniques, one of the most beautiful being laser cooling. It seems deeply counterintuitive to use lasers, which are beams of intense energy, to make something colder. But this is the strange magic of quantum physics. Scientists take a small cloud of atoms and place them in a vacuum chamber. Then, they fire precisely tuned lasers at the cloud from all 6 directions. The lasers are tuned to a frequency just slightly below the natural frequency that the atoms like to absorb. Because of the Doppler effect, an atom that is moving towards a laser beam will see the light as being slightly higher in frequency, the correct frequency for it to absorb a photon of light. When it absorbs that photon, it gets a tiny kick in the opposite direction, slowing it down. An atom moving away from the laser sees the light as a lower frequency and ignores it. By surrounding the atoms with this optical molasses, they are slowed down from moving at the speed of a jet plane to a crawl slower than a snail, cooling them to just a millionth of a degree above absolute zero. And at these unimaginable temperatures, the world ceases to behave in any way we would consider normal. The strange rules of quantum mechanics take over completely. For certain types of atoms, called bosons, something extraordinary happens. As they are cooled to within a whisper of absolute zero, their individual identities begin to dissolve. In the quantum world, every particle is also a wave. As the atoms get colder and slower, their waves get longer and longer until they begin to overlap. At a critical temperature, they all collapse into a single, unified quantum state, a new state of matter called a Bose-Einstein condensate. They cease to be individual atoms and begin to behave as one single, coherent superatom, all moving in perfect unison. It is as if a chaotic crowd of people, all shouting and running in different directions, were to suddenly freeze, and then all begin to sing the exact same note in perfect harmony. In our quest for an ultimate endpoint, for the final stillness of absolute cold, we discover not an ending, but a new and bizarre beginning, a doorway into the fundamental, wave-like nature of reality itself. As we approach this cosmic stillness in the confines of a lab, what does it tell us about the ultimate fate of everything? What is the final, quiet winter of the universe itself? In the unimaginably distant future, in a time so far from our own that the numbers lose all meaning, the last star in the cosmos will flicker and die. For trillions of years, it has burned through its last reserves of fuel, a dim red ember in an otherwise black and empty sky. And when its light finally fades, it will not be replaced. A final, endless winter will descend upon the universe, a cold and a darkness that will never again be broken. We journey now, forward in time, on a voyage to the end of everything. The rich, vibrant tapestry of galaxies that fills our night sky has long since dissolved. The stars, one by one, have exhausted their fuel and cooled into their final, quiet forms. White dwarfs that slowly fade to become cold, black cinders, massive neutron stars that spin down into silence, and the great, patient black holes that have swallowed their neighbors. The universe has become a vast, cold, and thinning soup of these stray, dead objects, drifting like lonely ghosts through an eternal, silent darkness. The great, energetic, and youthful age of the cosmos is over. This slow, inevitable slide into cold and darkness is a consequence of one of the most fundamental and inescapable laws of physics, the second law of thermodynamics. This law tells us that in any closed system, such as our universe, the total amount of entropy, which is a measure of disorder or randomness, will always tend to increase. Heat, which is a useful concentrated form of energy, naturally flows from hot objects to cold ones, and never the other way around. Think of a hot cup of coffee left in a cool room. The heat from the coffee does not stay put. It naturally spreads out, warming the air, until the coffee and the room are the same temperature. The total amount of energy is the same, but it is now dispersed, disordered, and far less useful. You can no longer use that faint, distributed warmth to power anything. The universe, on a grand scale, is doing the exact same thing. The hot, concentrated energy of the stars is constantly radiating out into the cold emptiness of space. The universe is, in essence, a cooling cup of coffee. The timeline of this future is drawn in eons. After the last stars die, the universe enters what is called the degenerate era. The only objects left are the compact, degenerate remnants of stars. Over timescales that dwarf the current age of the universe, even these objects will decay, and many will be consumed by the supermassive black holes that lurk at the center of what were once galaxies. The universe will enter the black hole era, a time of near-perfect emptiness, punctuated only by these gravitational monsters. But even the black holes are not eternal. As Stephen Hawking discovered, they too will slowly evaporate, leaking their energy back into the void over unfathomable stretches of time through a process known as Hawking radiation. A supermassive black hole might take a googol that is a 1 followed by 100 zeros of years to finally disappear. And after the last black hole has radiated away into a final puff of low-energy particles, the universe will at last approach its final state of thermodynamic equilibrium. This is the heat death. It will be a near-perfect vacuum, expanded to an unimaginable size, filled only with a thin, diffuse bath of stray photons, neutrinos, and other elementary particles. The temperature will hover just a tiny, irreducible fraction of a degree above absolute zero, and it will be the same everywhere, forever. In this state of maximum entropy, no more work will be possible. No structures can form. No information can be processed. The very arrow of time, which is so dependent on the increase of entropy, will lose all meaning. It will be a state of perfect, peaceful, and eternal stillness. We are left with a gentle, and perhaps melancholy, thought. If this cold, silent equilibrium is the ultimate fate of all things, what then is the meaning of the brief, warm, and brilliant flash of life and consciousness that we are now experiencing? Perhaps its profound preciousness lies not in its permanence, but in its transience. Perhaps the beauty of the song is that it has an ending. But is this final, universal ice truly the end? Or could it be that at the very edge of nothingness there is a glimmer of a new beginning? Think again of the intricate, fern-like patterns that frost makes on a cold window pane. From the simple physics of water crystallization, an endless and beautiful complexity arises. What if the universe itself is just such a pattern? What if the entire cosmos, with all of its galaxies and stars, life and consciousness, is a kind of magnificent crystal that has frozen out of the void? We are floating now, not in a specific place or time, but in a conceptual space, contemplating the final state of the universe. We are in the vast, cold, and nearly empty vacuum of the far future. It is a state of almost perfect stillness, but almost is not the same as perfect. For even here, in the quietest quiet imaginable, the universe cannot help but shimmer with a subtle, invisible, and incessant energy. This is the strange and wonderful truth of quantum mechanics. The vacuum of space is not truly empty. It is a roiling, seething foam of potential, a quantum field where pairs of virtual particles are constantly bubbling into existence and then annihilating each other in flashes too brief to measure directly. This process gives the vacuum itself a baseline level of energy, a zero-point energy that can never be removed. Even at absolute zero, this quantum jitter would persist. The universe can never be truly, perfectly still. This persistent quantum restlessness in the final void opens the door to some of the most speculative and awe-inspiring ideas in all of science. While our current understanding points to the heat death as a final, permanent state, some theories wonder if this is the entire story. Could a random quantum fluctuation in this cold, empty universe, over an almost infinite amount of time, spontaneously become large enough to create the conditions for a new Big Bang? It is a fantastically unlikely event, but in an eternity, the fantastically unlikely can become an inevitability. It is the idea that the universe could be cyclical, that our cosmos could be one in a long, perhaps infinite, line of universes, each one born from the cold ashes of the one that came before. It is a deeply compelling thought, that the end is also a seed. We can also think of it through the metaphor of crystallization and patterns. The beautiful, branching structures of a frost pattern, or a snowflake, are examples of what we call fractals. They are infinitely complex patterns that are generated by repeating a very simple rule over and over again. The rule for a snowflake is simply how a water molecule attaches to a growing ice crystal. And yet, from that simple rule, a universe of unique and breathtaking forms is born. Perhaps the fundamental laws of physics are like the simple rules of crystallization, and our entire universe, in all its staggering complexity, is the grand fractal structure that emerged, or froze out, from the incredibly hot, simple, and symmetric state that existed just after the Big Bang. As the universe expanded and cooled, the fundamental forces of nature separated from each other, breaking the initial symmetry, just as the smooth symmetry of water is broken when it freezes into a structured, six-sided crystal. And so, we are left with a thought that gently transforms the melancholy of the universe's end into something more like hopeful wonder. An end might not be a true end. A state of ultimate cold and stillness might not be a state of nothingness, but a state of pure potential. Just as a frozen seed in the Svalbard vault holds the perfect, sleeping blueprint for a new plant, perhaps the cold, empty, and final state of the universe holds the quantum potential for a new cosmos. The final, eternal silence that we envisioned might not be the end of the story. It might just be the profound and necessary quiet that must fall before a new symphony, with new laws and new possibilities, can begin. We have travelled from a single snowflake to the end of time and back. Now, let us bring our journey home, from the vastness of the cosmos to the universe we hold within ourselves, to the strange and beautiful ice of our own memories. There are moments in your life that are frozen in time, as clear and perfect as an ancient insect caught in amber, a memory of a particular slant of afternoon light in a room you have long since left, the sound of a loved one's laughter, echoing in perfect clarity, the feeling of a specific kind of happiness, so pure and complete that you can almost taste it. These moments are not like the rest of our memories, which flow and blur together like a river. They are crystalline. They are static and perfect. What is this strange and beautiful ice of memory? Let us drift, now, inward, into the quiet, vast landscape of our own mind. Search for one such memory. Perhaps it is a childhood winter morning. You can feel the satisfying, muffled crunch of your boots in freshly fallen snow. You can see the plume of your own breath, a fleeting white ghost in the sharp, clean air. The memory is not a film that you are watching. It is a place that you can inhabit. You can pause it and look around. You can examine the intricate, six-sided patterns of the snowflakes on your woolen glove. You can feel the cold on your cheeks and the warmth of your heart. It is a moment, rescued from the relentless flow of time and held in a perfect, frozen state. This feeling of permanence is the result of a beautiful and intricate biological process. When you first experience a moment, it exists in your brain as a short-term memory, a fragile and temporary pattern of electrical signals firing between your neurons. It is unstable, like liquid water, easily disturbed and quickly forgotten. But if the moment is important enough, the brain begins a process of stabilization called memory consolidation, much of which happens while you sleep. The brain replays the neural pattern of the experience, and with each replay, it strengthens the physical connections, the synapses between the neurons involved. It is like a well-trodden path in a forest, growing clearer and more defined with each pass. Over time, this process transforms the fleeting electrical pattern into a stable, long-term structural change in your brain. The memory has, in a very real sense, crystallized. It has gone from a liquid to a solid state, an enduring part of the architecture of who you are. Some memories crystallize with a particular, startling intensity. These are what scientists call flashbulb memories. They are the exceptionally vivid and detailed memories we have of the moment we learned of something deeply surprising, consequential, or emotionally arousing. The brain has a special mechanism for these moments. Your emotional center, a small, almond-shaped structure called the amygdala, works in close partnership with your memory formation hub, the hippocampus. During a moment of high emotion, the amygdala essentially shouts to the hippocampus. This is important. Remember this. It floods the system with neurochemicals that enhance the encoding process, searing the memory into your mind with what feels like photographic precision. The memory of where you were, what you were doing, who you were with, it all feels as though it is frozen in time with a single brilliant flash of light. And yet, here is the final, gentle paradox. Despite this powerful feeling of crystalline perfection, our memories are not flawless recordings. They are not static objects that we retrieve from a library. Memory is a creative, reconstructive process. Every single time you recall a memory, your brain is not simply playing it back. It is actively rebuilding it from its stored fragments. And in that act of rebuilding, the memory can be subtly altered. It can be colored by your current mood, reshaped by your later experiences, or softened by the gentle erosion of time. Our frozen memories, our most cherished moments, are not perfect. Objective records of the past. They are beautiful, but flawed, ice sculptures. And perhaps their beauty lies precisely in this fact, that they have been, lovingly and unconsciously, shaped by our own hands over the years. They are our personal ice cores, a layered, imperfect, but deeply true record of our journey. They have shaped the landscape of who we are, and given meaning to the warmth and the cold of our lives. We have travelled from the first crystal in the sky, to the last star in the cosmos, to the quiet memories of our own heart. What is the final, gentle truth that this long journey through the world of ice leaves with us, as we now drift peacefully towards sleep? The world outside may be spinning, the day may have been filled with motion and with noise, but here, in this quiet moment, we can find a stillness, a peace as deep and as profound as a world locked in ice. Let us return, for one last time, to the image that began our journey, the vast, frozen lake under a canopy of stars. The sun has now set, and the last embers of twilight cast a soft, warm, rosy glow on the cold, blue surface of the ice. The world is hushed. The air is still. Everything is at rest. There is a feeling of wholeness here, of a great and beautiful cycle, having reached a moment of perfect, peaceful completion. This cycle, the journey of water, is the story we have followed all along. We saw the water vapor in the high atmosphere, needing a seed to begin its transformation into a delicate crystal of ice. We saw that snowflake fall and join a collective, becoming a protective blanket on a lake, a powerful glacier that sculpts a continent. We know that eventually, that ice will melt, flowing in a river to the sea, where it will evaporate into the air once more, waiting to return as a new crystal in a new winter. This is the great pattern of existence. The stars themselves follow this cycle, born from clouds of gas and dust, burning brightly for billions of years, and then returning their elements to the cosmos, providing the raw material for new stars, new planets, and new life. We have even contemplated the idea that the universe itself might be part of this rhythm, born from the cold void, and perhaps, one day, giving birth to a new cosmos from its own quiet end. This journey has taught us the profound philosophy of stillness. In our waking world, we often think of stillness as an absence, an emptiness. But the world of ice has shown us that this is not true. The stillness of the frozen lake is not an absence of life, but its protection. The stillness of the seed in the Arctic vault is not an absence of potential, but its perfect preservation. Stillness is not an end. It is a state of deep rest, of restoration, of gathering strength for the inevitable return of warmth and activity. And this, of course, is the very nature of the sleep that you are now so close to. Sleep is our own personal, daily winter. It is a necessary retreat from the world, a time of quiet and withdrawal. But it is in this quiet that the most profound work is done. It is in sleep that your body heals and restores itself. It is in sleep that your mind consolidates the important memories of the day, transforming the fleeting moments into the enduring crystals of who you are. Sleep is the gentle freezing of the river of our consciousness, allowing it to find its own quiet equilibrium, preparing it for the warmth of a new morning and the beginning of a new day. And so, we end our journey here, in this place of peaceful balance. We have seen that the cold is what gives the warmth its meaning. The silence is what gives the music its beauty, and the stillness is what allows for the graceful return of motion. The world of ice is not a world of endings. It is a world of patient, beautiful, and profound waiting. Thank you so much for joining me on this quiet journey tonight. I hope it has brought you a measure of peace and comfort. If you have enjoyed our exploration, please consider leaving a kind comment, liking this video, or subscribing to the channel for more gentle stories. It is a small gesture that helps this peaceful space grow. For now, there is nothing left to do. Let the images of the snow, the ice, and the stars gently fade. Let the stillness of the frozen world become your own stillness. May your rest be deep and your dreams be peaceful. Good night.